Okay, in this video, we're going to go over the practice exam for exam 2. So let me share. All right, hopefully you can see this, and that everything's working. So as I said in the announcement, this problem the practice exam consists of 17 problems, but there will be much less on the actual exam. There's just a lot of material, and I'm not exactly sure which material I'm going to cover, but we do need to know all of this anyways, because for the final, we will definitely be covering all of the material. So that's yeah, just a warning, not a warning, but just to allay your fears, I guess. The actual exam will not consist of this many problems. So let's just start. Let's start right away. We'll start with problem 1. So in problem 1, we have to perform long division on the following fraction, or we want to compute the following fraction using long division. So we want to compute this. I'm going to do long division on this and then identify the quotient and the remainder. So to do that, we have to set up the problem in the following way. So we put x minus 1 here, and then we put x squared plus 2x here minus 5. And then recall how long division works. To figure out how this term divides into this, there's an algorithm, first of all, and the algorithm states that you start with the leading term of this and divide into the leading term of that. So x into x squared gives me x. And then the next part of the algorithm states that you take that quotient you just computed, which is x, and you multiply it back through by x minus 1 and subtract the result. So you get x times x minus 1 is x squared. So negative x squared because I'm subtracting. And then x times negative 1 is negative x, but then I'm subtracting, so I get plus x. So now I combine these together, I get x squareds go away, and then I get 3x minus 5. And then I do the algorithm once again, and you perform the algorithm until what you end up with is a polynomial of degree less than polynomial you're dividing by. So these are both first degree polynomials. So the algorithm states that I can do the process one more time. So I take the leading term of this and divide into the leading term of that. So x divided by 3x gives me plus 3, and then I multiply the 3 back through x minus 1, and then I subtract. So I get 3 times x is 3x, but I'm subtracting. And then I get 3 times negative 1 is negative 3, but I'm subtracting, so it'll become positive 3. And then I have negative 2. So x plus 3 is the quotient. And I guess negative 2 is the remainder, you just say. So what that means is that x squared, this step's not strictly speaking required, but it's just good to know this, how this computation allows you to decompose the fraction in the following way. What you get is x plus 3 plus negative 2 divided by x minus 1. And then this kind of actually tells you, if you remember a section on rational functions, you can there we talked about how there are horizontal and vertical asymptotes, and then there's also the case of oblique or slant asymptote. and you find these asymptotes by computing limits, basically. So this calculation reveals that this rational function right here has, a slant asymptote of x plus 3. So you'll have this line that's neither vertical nor horizontal, but at some angle that will that this rational function will approach. So you can plot this and you can actually see this. Maybe I'll just actually plot it right now. So just so you can see that. I'll use Wolfram Alpha. I actually encourage everyone in class to use this just to check your answers and to figure out if you're on the right spot, or if you have a hard time graphing something, like you're not exactly sure how it's supposed to work out. If you want to figure it out, you can use Wolfram Alpha, and it's pretty helpful. Just to like compare your answer, basically. So I'm using Wolfram Alpha right here. I don't know if you can see this. Hopefully you can. Let me try. Make sure I'm sharing it the right way. Yeah, I'm sharing the screen, not OneNote. Okay, so I guess hopefully you can see this. Oh, oops, no, that's not what I want. Okay, anyways, here's the plot. So I'm plotting this function. You can see right here, there is, so first of all, it has because there's the root of the denominator is 1, so the function is not defined at 1, there's a singularity at 1. There will be this vertical asymptote at 1. Then there's a theorem that says because the degree of the numerator is bigger than the denominator, there will be no horizontal asymptotes, right? So no horizontal asymptote. But there is that slant asymptote right here. Actually, I can plot that. I can plot that and x plus 3. So you can see the graph gets arbitrarily close. So the purple line is x plus 3, and then the rational function gets arbitrarily close as x goes to positive and negative infinity, but it never touches it actually. Okay, so that's the first problem, but all we needed for the first problem is this part here. This is all that we were required to find. Oops. This part right here. So do the division algorithm, and then identify a quotient in the remainder, but also keep in mind what these calculations are for. Why do we care about these calculations? So that's the first problem. The next one is putting a certain quadratic function into standard form and then graphing it. So this is number 2. Oops. So the function is f of x is equal to 3x squared minus 6x plus 1. So to put it in standard form, we need to complete the square, and then once we've completed the square, we'll be able to gather a lot of information about this graph, or the function, which will enable us to graph it. So first of all, to complete the square, we need to factor out 3 from the whole expression. So we get x squared minus 2x plus 1/3. And now I'm going to complete the square on this expression. So I have 3. So to do that, I take half of this coefficient. So half of the middle term coefficient, and that's -2. I add it, so I get -2/2 squared, and then I subtract it. So let's add the quantity and subtract it, and then there's the 1/3, and this is all happening within the parentheses. Don't forget that this is 3 times this whole thing. So this right here will be -1, and so let me just write it out. So we get plus -1 squared. I don't want to square it because then it won't be clear how I'm factoring this. Oh, sorry, there should be negative here. This I will square and I will cancel the negative. So I get negative. So this will be -1, but square gives me +1, but there's this negative in the front, so I have -1. And then plus 3. And now I can factor this part to get x minus 1 squared. And then negative 1 1/3 will be negative 2/3. And now I can distribute 3. So if I distribute 3, I get this. So first of all, remember what, so this is going to be a transformation of x squared. So first of all, let's just remember what x squared looks like. It looks something like this. So first of all, this is like a stretch. I don't really, in terms of just graphing, it's hard to really, because I want a rough sketch, so it's really hard to keep this factor into account. It's really going to be like a vertical stretch of this, and so it's going to kind of become narrower, but I don't really care about that. If you don't have to be precise with that. All I really care about is the 1 here and the 2 here. These will correspond to shifts. This is like a stretch factor, so if you, yeah, so it will actually it should make the graph actually not shrink it, but make it wider. But I don't care about that. So if you don't put that in account, that's all right. All I care about is that you shift it appropriately. So first of all, the negative 1 means you shift to the right 1 unit, and then the negative, so the negative 1 inside the parenthesis. So you're subtracting 1 from the x and then squaring. So that means that you're shifting to the right 1 unit. And then the fact that you have 2 on the outside, negative 2 on the outside, corresponds to a vertical shift, and 2 means you shift down 2 units. So a rough sketch of this would be something like you go over 1 unit, so maybe the 1 unit is there, and then you go down 2 units, 1, 2, and so the vertex, this will tell you where, well, first of all, this right here means the vertex is 1, negative 2. So that's the point kind of where it opens. And then the 3, because we have, so I guess the only reason I care about the 3 is to tell you whether it opens up or down. Because 3 is positive, that means it opens upward. So maybe open up like, I don't know. Wait, let me look at the problem. What do we need to know? Actually, we don't mention x and y intercepts, but we can find those. So y-intercept will be, you plug in 0, and then you get negative 1 squared, 3. So negative 1 squared is 1, then times 3 is just 3, and then minus 2 is 1. So it crosses at 1 up here, maybe. All right, so I'm going to actually just redo it. So this is, let me just say that this is y-intercept. What about the x-intercept? Well, that's when I set the function equal to 0 and I solve for x. Again, this part's not required, but in the problem, I'm finding the x and y-intercepts. Maybe I would change the problems because you can get a graph that's a little bit more precise. So I can solve for x. So I added 3 to both sides, and then I'm going to divide, I added 2 to both sides, and then I'm going to divide by 3. And then I'm going to take the square root. So we get x minus 1. So maybe this doesn't help actually, because, so I take the square root and I get plus or minus square root of 2/3. And then I can add 1 to both sides. I get 1 plus square root of 2/3. So you have an x-intercept to the left and to the right of 1, basically. All right, so maybe that's enough to draw the graph. Is there a way of doing it? Like, I don't want it there though. Yeah, let's see, can I? Can't really do that. As you can tell, I don't really use OneNote a whole lot. So, all right, well, anyways, that's enough. I'll just draw my best line right here. All right, so we have the vertex is 1, -2. So we go over 1 unit and then down 2 units, 1, 2. And then at 1, 0, we intersect. And then just around, so at just to the left of 1, there's a root, and then to the right of 1, there's a root. So maybe this is going to look awful, especially because the writing tablet is not like drawing with actual pen on pen and paper. So, but it looks something like this. I don't know, something like that. It should be a little bit rounder, but you get the idea. Let me actually use Wolfram Alpha again. So we want to plot 3x squared minus 6x plus 1. So let's see, does our work align with what they with what Wolfram's plotting? Yeah, so see right here, there's y-intercepts at 1. Here's the vertex. You go over 1 unit and then you go down 2 units. So there's the vertex. It opens up because 3 is a positive number. And then we have x-intercepts just to the left and right of 1. Okay, so let's just review this again. So the problem is to put the function in standard form. So we complete the square, and that you do that by completing the square. And then once you are in standard form, right here, you can immediately identify the vertex. Oh, I didn't mention whether it has a minimum or maximum. So, so you have you can identify the vertex. And then you can also identify whether it has a minimum or maximum. So this is, let me get rid of this right here so I can write down the minimum and the maximum. So yeah, this once you're in standard form, you can clearly see that it is just a transformation of x squared, and this will have a minimum because 3 is 0, and therefore graph opens up from the vertex 1, -2. And then maybe on the exam, I'll have you find the x and y intercepts also. I don't know. I haven't written the exam yet, but the exam will be similar. And then this is an awful plot, but it's roughly what's going on. And then we saw when you use Wolfram Alpha, you can get the plot. And the plot of it just basically aligns with what we found algebraically, using algebraic methods to analyze the function. Problem 2, let's move on to problem 3 now. So number 3 is we have a function and we want to factor it to find the roots, and then try to identify the plot of we have these 4 options and we want to identify the graph of this function. So function is x cubed plus x squared minus 20x. So first of all, there's a common factor of x, so we can take that out. So we have what we're left with is x squared plus x minus 20. And now this is a quadratic, and we can actually factor this. We can factor this quadratic. So we just need to find the factors of 20, whose sum is 1. And that's going to end up being 5 and negative 4. So x squared, and then negative 4x plus 4x gives you the x in here, right here. And then positive 5 times negative 4 gives you the negative 20. So this implies that the roots are 0. Oh, let me just write them in increasing order. So negative 5, 0, and then 4 are the roots. And then also leading coefficient positive. So that means what that means then is that, let me just write down the conclusion from that, is that when you take the limit as x goes to positive infinity of the function, you're going to go to infinity, and when you take the limit as x goes to negative infinity, the function will go to negative infinity. So let's look at the plot and try to, based on this information, try to identify it. So we need roots of negative 5, 0, and 4. So first of all, let's look at the end behavior. That will kind of rule out which graphs. So as x goes to negative infinity, this for graph A, the function's going up to negative infinity, positive infinity, actually, I should say. And the function's, as x goes to positive infinity, the function's going to negative infinity. So that will not be the sort of behavior we need. For this, the function, for B, the function goes to, and the same thing for D. The limit behavior of the function is not the right limit behavior, because as x goes to negative infinity, the function goes to positive infinity, and as x goes to positive infinity, the function goes to negative infinity. So this is the function. The graph of the function will neither be A or D, because you're looking at the limits. However, B and C have the right limiting behavior. As x goes to positive infinity, the function goes to positive infinity, and as the x goes to negative infinity, the function, this graph goes to negative infinity, and the same thing for C. So the options we're left with are B and C, but now we have to look at the roots to see which function, which graph actually corresponds to our function. They both have 0 as a root, so that's not helpful, but you can see that the root of this, so if you count the tick marks, so it's 1, wait, the tick marks are kind of weird. One. It looks like they're going by 1/2. So this is negative 1/2, 1, 1, negative 1.5, 2. So what we have is 4 here, 4. Okay, so I think this is actually kind of a confusing graph. Oh, I see. There's an easier way to do this. So we know that 4 is a root, right? We factored the polynomial, so the roots are negative 4, 5, 0, and 4. If you look at B, 4, the graph does not cross the root 4, so B is not the right option. So the correct option is C. So for problem 3, the answer is C. Let's see. And we use the limiting behavior and we use the roots to determine it. So I need to stop sharing for a second. Hold on. Okay, so let's work on problem 4 now. Let me share my screen again. So in number 4, we're given the function f of x is equal to 2x minus 1 minus 1/2. We want to find the x and y intercepts and the horizontal asymptote, and then from that we want to graph the function. So let's look at the x-intercepts. So we know actually there's only going to be one x-intercept because this function is injective. That is, there's only one value of x that makes this function 0. So we don't need to say x-intercepts. We know that's not the case for polynomials. Sometimes a lot of polynomials can have multiple roots or x-intercepts, but exponential functions are injective. So there will only be one intercept. So to find the intercept, we have to set the function equal to 0 and solve for x. So we get we can add 1/2 to both sides. And then at this point we can well, I guess we could take the log base 2 both sides and then cancel things out, or we could just, as I said, use injectivity of the function, exponential function. We could take 1/2 and write it as 2 to the -1, and then because 2 at the exponential function is injective, it implies that this exponent equals this exponent. So we can immediately conclude that x minus 1 is equal to -x. So that implies x is 0. And maybe you could have guessed that from right off the bat. Which is fine too. You can just say x is the root because, you know, if you put 0 in, you obviously get 0. So this is the x-intercept. What about the y-intercept? Well, to do that, we have to set the function equal to 0. Or I'm sorry, we have to evaluate the function as 0. And as you can see, it's going to be 0 again. So the x and the y-intercepts are the same. So in other words, it just passes through the origin. So 2 to the 0 minus 1 is just 2 to the -1, which is 1/2. So we have 1/2 minus 1/2 is 0. So 0 is 0 both x and y intercept. And then to get the horizontal asymptote, let's just recall the graph of 2 to the x itself. So 2 to the x looks something like this. It has, remember, this is the general form of basically every exponential. It opens up like this, and then it passes through. So this is a plot. This is going to be a plot of 2 to the x, and it passes through 0.101. It opens up like this. So you can see that as x goes to -infinity, the graph goes to 0, so it approaches 0. So x-axis is the horizontal asymptote. The x-axis is just described by, oh, sorry, this is really awful looking. So the x-axis is just described by the line y is equal to 0. So y is equal to 0 is the horizontal asymptote. Now, so our function is just going to be a transformation of the exponential function 2 to the x. So we have -1 here means it corresponds to a horizontal shift to the right 1 unit, because we're subtracting 1 from x and then raising 2 to that power. And then the 1/2 on the outside when we subtract 1/2, that corresponds to a vertical shift downward 1/2 unit. So we can transform the graph and we can, with that in mind, we can transform the graph and plot it. So we know that it passes through here. And when you transform the function, you also have to transform the horizontal asymptote. So if you shift the line, the x-axis over, you still just get the x-axis. But if you, that is, if you shift it horizontally, you still get the x-axis. But if you shift it vertically, you will change the asymptote. So the asymptote, when we shift this function down 1/2 unit, the asymptote also shifts down 1/2 unit. So that the new asymptote will be at -1/2. So maybe it's like right here. So y is equal to -1/2 horizontal asymptote. And then we know it passes through here and it has to approach it, this asymptote. So it goes like this. And then it just goes up like that. So I think that's all the problem. So yeah, I guess we can indicate let's label everything. We labeled a horizontal asymptote, but let's label the x and y intercept, which is actually the same. So it goes to the origin. And let's plot this using Wolfram Alpha. So we want to plot 2 raised to the negative, or to x minus 1 power, and then subtract 1/2. So let's see if we got something roughly the same. Yeah. So see, it goes through the origin, and actually let's also plot -1/2. So we plot this and -1/2, and it should approach that line. Yeah, see, it approaches the line as it goes out. So let's plot it from, I don't know, -10 to 1. Just to see it actually approaching it asymptotically. So yeah, see, we have 1/2, the line 1/2, and then as the function, as you go out to -infinity, the function gets arbitrarily close to the line 1/2. All right, so that's problem 4. Let's go through 5. So 5 is, we have the following function, and we have 4 graphs, one of which corresponds to the function. So we have f of x is equal to 6 minus e to the x. So first of all, let's remember e to the x. Well, e to the x is just exponential function. So let's plot e to the x. It's going to look like this. Oops. And then let's just perform each transformation individually or separately, I guess. So e dx looks like this. It goes up, crosses at 0, 1, as does every exponential function. So this is not right. It should be plot of e to the x, and then it asymptotically approaches the x-axis. The line y is equal to 0. So the first transformation we have to worry about is this negative. So we multiply by e to the x by negative. So let's plot that. E to the negative e to the x. When you multiply a function on the outside by negative, that corresponds to reflecting it over the x-axis. So the plot of this will look something like this. It approaches asymptotically as x goes to -infinity. It's not really curved. No, that's not good either. That's as good as I can get it. So it's just going to reflect. So it's going to cross at 0, -1, and then it's going to asymptotically approach. Oops. The x-axis as x goes to -infinity. And then, well, first let's write, so our function is 6 minus e to the x. Let's just write it like this. And then it'll be clear what the next transformation is. The next transformation is going to be a vertical shift upward 6 units. And that means that the asymptote goes up 6 units as well. So the asymptote is y is equal to 0. So now we have, we can actually finally plot f of x because we can combine all these transformations. So e to negative e to the x plus 6. And then we'll be able to select the right option. Let's see. Maybe that would be better. Something like that. So, there we go. So that the asymptote, the horizontal asymptote of e to the x is the y-axis, but we need to translate it up 6 units. So maybe it goes about here. Actually, I wonder if there's a dotted line. All right, let's redo that. Is there some sort of dotted line? Probably not. Nope. All right. Anyways. So this is the new vertical asymptote, and it's going to be y is equal to 6. I'm sorry, horizontal asymptote. And then, so we just need to shift this graph right here up to this asymptote. So it's going to go to something like that. And then it's going to intersect somewhere right here, and then somewhere right here. And actually, I think we're going to need to know. No, we don't. So let's look at the options now. So we can immediately rule out A and B because they just don't look like our graph. So the only options are B and D. But we can also rule out B immediately too, because B is, so the tick marks are 1 units, 1, 2, 3, 4, 5, 6. So this B, if B were the right option, that would mean that it would mean the graph goes through the horizontal asymptote, but they can't. It can only get arbitrarily close. So B is not the right option because this graph passes through the line y is equal to 6. D does not, however. So it gets the line. I don't know if you can see what I'm pointing at with the mouse. This tick mark right here is 6, and if you draw out the line, the graph just gets arbitrarily close but never passes through it. So the option is D. So for problem 5, the answer is D. All right, so let's look at number 6. So we want to find the x and y intercepts of ln, oops, ln of x plus 1 minus 2x. And then we want to, so we want the x and y intercepts and then the asymptote and then give a rough sketch. So let's look at x-intercept. Again, we know there's only going to be one x-intercept because the function is invertible, or it's 1-to-1, and the same thing with the y-intercept. So x-intercept is, we set the function equal to 0 and solve for x. So we add 2 to both sides, so we get ln of x plus 1 is equal to 2. And then we can exponentiate. I guess if you want, that's one way of doing it, to get e to the ln of x plus 1 is equal to e to the second power. But the exponential and the natural log function are inverses of each other. So these cancel out to give x plus 1 is equal to x squared, or is just equal to x plus 1, which is equal to e squared. And then I can solve for x to get x squared minus 1. And we can factor that like this if you want. This will actually tell, the reason why I factor this is because it will tell me that this is a positive number. So remember, e is something like 2.1 or 3 or whatever. But the point is that e minus 1 is a positive number because e is greater than 1. And then obviously e plus 1 is a positive number because the sum of two positive numbers is positive. So we have a product of two positive numbers, so it's positive. So this would mean that the graph crosses somewhere to the right of the origin. Now let's find the y-intercept. To find that, you set the function equal to 0. And then you get ln of 0 plus 1, with that becomes ln of 1 minus 2. And then ln of 1 is 0, so you get negative 2. So the graph crosses at negative 2. So let's just write down the function here so I don't have to keep scrolling back up. So it's ln of x plus 1 minus 2. So let's just recall the graph of ln of x and then just perform the suitable transformations. So we get, actually, let me do it this way again. So, oops. So this is a plot of ln of x, and that looks something like this. And it crosses right here at 1, 0. And it has x is equal to 0. That is the y-axis, is the vertical asymptote. All right, so now we're actually looking at ln of x plus 1 minus 2. So the plus 1 means we shift to the right 1 unit. So let's plot that. You don't have to do all these steps if you don't want to, like plot each one. You can do the transformations all at once if you can see it, but if you can't, you're not sure what the end result looks like, just do each transformation individually. So now we're going to just do the horizontal transformation, and the plus 1 means, so that's plot of this. The plus 1 means you shift to the left 1 unit. So let's plot that. So if you shift everything to the left 1 unit, you also have to shift the vertical asymptote. So maybe right here is 1 unit. And then I don't know where it's going to cross. Let's see. X is, I guess I'll cross at the origin. Set that equal to 0. Oh, I'm okay. Yeah, if you shift this over 1 unit, the root shifts over 1 unit, it goes to the origin. So this will look something like this. It'll cross through the origin at 0, 0. So everything, when you shift over, vertical vertical and horizontal shifts are rigid motions. So everything moves over the same unit, same distance. So the vertical asymptotes move, the horizontal asymptotes move, and even the graph itself moves, and in particular its root. So if the whole graph moves over 1 unit, in particular the root moves over 1 unit, so it'll move to the origin. So that's why this graph will look like this. And then finally, the last transformation is shift down 2 units. So now we can shift that graph down 2 units. So this will be a plot of the function itself, which is actually called g of x. So we have g of x is equal to ln x plus 1 minus 2. So now we can do this last transformation, shifting down by 2 units. So let's do that right now. Whoops. Oh. So if you shift downward, if you shift the vertical asymptote downwards, it doesn't move. So we'll still have a vertical asymptote at -1, just like right here. Now the x-intercept is going to shift down 2 units to here, say maybe. Here's 1, and then maybe here's 2. And then the graph is going to look the same, basically. It's going to go like this. Instead of passing through the origin, it is going to pass through, actually, it's going to pass through here. But also, we already determined the x and y intercepts. They are, well, -2. The y-intercept is -2, and then the x-intercept is e squared minus 1. So, and we said that e squared minus 1 is some positive number. So maybe it's over here. I don't know exactly where it is. So the graph will look like this. It's going to go up, and I'm going to try my best. And actually, let me just draw the graph and then put the x-intercept on. It's just easier. And then right here, we have e squared minus 1, comma 0, and this will be 0, comma -2. And then the y-intercept, the horizontal asymptote is x is equal to -2 is the horizontal, vertical asymptote, I'm sorry. And then just for shits and giggles, let's plot this in Wolfram to see if we got something that looks remotely like what we have. So we're plotting ln of x plus 1 minus 2. And then we can also plot and x is equal to -2. Maybe it doesn't understand that, actually. Oh, maybe I just need to do hand plot at -2. And that gives me a vertical horizontal line I want. Huh. Let me look it up. How how to plot a vertical line actually. Try that again. So we want to plot this. Maybe I'll say and plot x is equal to -2. I don't know why it's doing that. It's just giving me, let's say plot y is equal to ln of x plus 1 minus 2, and then plot x is equal to -2. I don't know. There's got to be a way to do this, but it's not. I don't know why it's not working. But anyways, you can see if you draw down. So 1, 2, 3, 4, 5. So 2 is right here. If you draw this line down, it's getting arbitrarily. The graph's getting arbitrarily close to it. All right. So let's move on to the next problem. This is number 7. The problems we just did were kind of the longest because these are like, actually there's 2 more plots. Actually, I spoke too soon. The more problems we're gonna work on are relatively quick though. So for number 7, we want to use the laws of logarithm to expand the following expression and then simplify it if possible. So we have log base 3 of 7x cubed times y. So first we need to expand. We need to use that multiplication to sum property. So we have 7 times x to the 3rd times y. So we can split it up as log base 3 of 7 plus log base 3 of x cubed plus log base 3 of y. This piece can't simplify any further, so we'll just write that down here. Now this one can, the middle term, because we have x to the 3rd, so we can use that property of exponents to write the exponent as coefficient. And then again, for this one, we can't simplify any further, so we get this, and we're done. So that's 7. For 8, we need to use laws of exponentials in this case to simplify the following. So we have e to raise to the 2 plus natural log of x cubed plus x squared. So the first thing is that we need to use the fact that e to a sum is the product, becomes a product like this. So if you have e to the a plus b, it becomes e to the a times e to the b. So we have 2, the a in this case is 2, and then b in this case is ln x cubed plus x squared. So we get ln, so we get e to the 2nd power times e to the ln of x cubed plus x squared. And then we need to use the fact that the natural log and the exponential are inverses of each other, so they cancel, and then what we get left is this, the argument of the logarithm, which is that, and that's that will be the answer for number 8. For number 9, we need to solve. We have these 2 equations. It's 2 parts, and we need to solve for x and y respectively. So in part A, we're solving for x, and we have the following. So there's a lot of ways you can do this. You can just use what the definition of x, the log is. It's basically the power log base. So in this case, log base 4 of 2 is that power you need to raise to 2 to get to the number 4. And in that case, that'll just imply that. But if you don't remember the definition exactly, but you remember that exponential and logarithmic functions are inverses, you can exponentiate both sides. So if you exponentiate both sides, you get to the fourth power. You want to raise everything to 4. You get this. And then you have 4 to the x. And then, oh wait, this is not right, actually. That's nonsense. Well, let's just exponentiate it, and then I'll remember the definition. So 4 and the log base 4 cancel, and you get 2 is equal to 4x. And then you can, I guess, write it like this. And then you use the fact that the function's injective to get 1 is equal to 2x, and then that will imply x is 1/2. So the one method is to just exponentiate, take 4 and raise it to this side and this side. The other method is just to use the definition, and the definition is the log base. So in this case, log base 4 of 2 is the power you raise. I got it backwards. It's the power you raise 4 to get the number 2. And that will be 1/2, right? So more generally, log base a of b is the power you raise a to get b. So in other words, that says that a log base a of b is equal to b. It's that power you raise. So in this case, you have to raise 4 to the 1/2 power. In other words, you have to take the square root in order to get 2. So log base 4 of 2 evaluates to 1/2. So therefore, x is 1/2. So that's one way to do it. Or if that's too confusing, just do this exponentiation. And this trick of exponentiation shows up a lot. Anyways, it's a lot easier, I think. So what you do is you just, whatever the base is, raise both sides of the equation to that power, to that base. So I'm going to take the equation, and I'm going to take 4 and raise it to log base 4 of 2, and then x and raise 4 to x. Well, 4 and log base 4 cancel, so you get 2 is equal to 4 to the x. But 4 is the same thing as 2 to the x power. Maybe I should write that out. So 4x is equal to, I kind of did that fast, 2 to the 2 to the x. But remember, when you raise a power to a power, you just multiply the powers. That's how I got this right here. And then we have 2 to the first power is equal to 2 to the 2x power. And then by injectivity, we can say those powers are the same, and then we just solve for x. So either way will get you the answer. You can either just go back to the definition of a logarithm, which is right here, and then just answer that question of which power you need to raise a to get b, or you can just exponentiate. And I think exponentiating is easier. So that's number 9 part. B, part A. Now we're going to do part B, and we're going to solve for y in this case. So again, you can use the definition and figure out what y has to be using the definition of the logarithm, but I think it's just easier to exponentiate both sides. So I take 4 and raise it to this power, and 4 and raise it to that. So 4 log base 4, they cancel out, and I get y is equal to 4 squared. 4 squared is 16. So that's, I think, a lot easier than remembering a slightly confusing definition. So that's number 9. Let's do number 10. So number 10, we want to solve, we have 2 parts again. And we want to solve for x in both cases. So part A, the equation is 10 to the 3x minus 1 power, or 4 power, is equal to 1/10. Well, we can write 10 as, again, we're going to just use injectivity. It all comes down to exponentiating and then using injectivity of either the logarithmic function or the exponential function. In this case, we're going to use injectivity or of the exponential function. For those of you who might not remember, the book uses the term one-to-one. You can talk about one-to-one functions, but those are the same as injective functions. The two terms mean the same thing. So I have 10 to the 3x minus 4th power, and then I have 10 to the negative 1 first power. So that because the exponential function is one-to-one or injective, the powers have to be the same. And then I can solve for x. So I add 4 to both sides, so we get 5. And then I can divide by 3 to get 5/3. And then for part B, again, I'm going to either when you deal with these types of equations involving logs and exponentials, you're either going to use exponentiate or use the fact that these functions are injective. So you can either exponentiate. So exponentiate. So if I just take e and I raise it to this power, and then I take e and raise it to the 0th power. E, ln, e and the natural log cancel out. So I get x squared minus 3. And then e to the 0 is 1. I can add 3 to both sides to solve for x. And then I can take the square root, to get plus or minus 2. Now, we have to be careful though, make sure that these solutions make sense. Can I actually plug those in? The answer is yes. If I plug in plus 2, I get 4 minus 3, which is 1. And then ln of 1 does in fact equal 0. And then for the other root, I can plug in negative 2 as well. So if I take negative 2 and I square, I get square of negative 2 is 4, and then 4 minus 1 is 0. 4 minus 3 is 1, and ln of 1 is 0. So these solutions make sense. So one way to find those solutions is exponentiate. Another way is to use the following fact: the fact that the function is injective. So again, solving these types of equations either reduces down to exponentiating or using the fact that the functions are injective. Ln turns out, and we already know this actually, ln of some number, say y, just to use a different number than just a letter than x, is true if and only if y is equal to 1. Well, why do we know that? Well, we know ln of 1 is 0. And because the function is injective, that's the only solution to this equation. So we can say ln of x squared minus 3 is 0 if and only if x squared minus 1 is equal to x squared minus 3 is equal to 1, and then solve just as we did here. So you can either exponentiate both sides or just use this fact that the natural log of some number is 0 if and only if that number is 1. So that was part. Oh wait, oops, did I skip a problem? Yes, I think I skipped a problem. Oh, I looked at the wrong. So actually, I looked at the wrong problem. So this is not problem 10 part B. This is actually problem 11. Maybe you can see that already. So this is number 11. I kind of did these out of order. Whoops, I didn't realize it. So I just did number 11, part B. So now let's go back to part 10. So let's do number 10, part B. So for this one, we need to solve the following equation for x. And we're just going to use injectivity, or the fact that the exponential function is 1-to-1. So that from here, the function is set up nicely that we can immediately include that the powers are the same. So we can put all, we have a quadratic, so we want to either factor or maybe use quadratic formula. But in order to do that, we need to get all the x's on one side. So if we can subtract x from both sides to get 3x on the left-hand side, and then we can add 2 to get this. And then actually we can factor. What we get is negative 2 and then x minus 1. And I'm sorry, actually these are pluses. So the solutions of this equation are -1, -2, and -1. Now we can go back to part. Now we can move on to part, our problem 11. We already did part B, so we'll just do part A. So for this, we want to solve the following equation. So we have log base 5x plus log base 5x plus 2 is equal to log base 5 of 35. So we're going to first use the multiplication to sum property of logarithms to write this, the left-hand side as x times x plus 2. And then we'll have this. The right-hand side will be the same. And now we can use injectivity, or the fact that the one-to-one property of the logarithm to cancel out the logs. And then I'm gonna FOIL this. So I'll get x squared plus 2x is equal to 35. And then I can subtract 35 from both sides. And I think this factors as, let's see, x minus 5 times x plus 7. So this will imply that x is equal to -7 or 5. However, -7, not an actual solution, because you cannot plug. You cannot take the logarithm of a negative number. Look at our original equation. It's we have natural log of x. So if you plug in x is equal to 7, you'll have natural log of base 5, log base 5 of -7, and that's not defined. So you have to rule this out. So the only solution is 5. All right, so now let me stop sharing for a second, actually. Okay, so let's work on 12. Share my screen again. So number 12, we have t-value of 2/3 pi. We want to find the referenced angle. It's actually not reference angle, it's reference number. These end up being angles. We're going to go through chapter 6, and we're going to find a new system of units to measure angles. So we have the familiar degree measurements for angles, and we're going to define a radian, and it's going to end up being an arc length. defined in terms of an arc length. And these t values I'm giving you are basically arc lengths. They tell you how far to travel along the circle. So to do that, we need to figure out. So first of all, this point is going to be related to pi over 3. So these are we need to think about the coordinates of this point. But first of all, we just need to figure out what quadrant we're in. Because once we do that, we can figure out the coordinates. They'll be based on the coordinates of these, but maybe pluses or minuses somewhere. So we have our unit circle. I should always draw the unit circle and all those values, the ones in the first quadrant. So the 2/3 pi means that we're going 2/3 of pi. We know that pi means you travel along this way, and then you land here at the point -1, 0. 2/3 pi means that you don't go quite pi, you just go a little bit less, but you go more than pi over 2, which corresponds to the point 0 and 1. So you end up landing like about here. So we have maybe pi over 3 corresponds to this point, but then pi over 2 corresponds to this, maybe 2/3 pi, I should say. 2/3 pi corresponds to this. Now the coordinates of this point are √3 over 2, 1/2. So the coordinates corresponding to that, so this particular t value, the coordinates for this are well, in the second quadrant, x coordinates are negative, but the y coordinates are positive. So it'll be negative √3 over 2, 1/2. And let's see, I got the unit circle I pulled up, so let's make sure it's right. I did it wrong. Whoops. This is why you should always draw your unit circle. So I accidentally wrote the coordinates for pi over 6. So let's do this again. So we're actually it's still roughly the same. Actually, I shouldn't even done that because it's just I drew on the wrong spot. We're still in the second quadrant. All right, let me just do it again. We're still in the second quadrant, but we're actually looking at pi over 3, and that ends up being here. I wrote something down here. That's pi over 6. Pi over 3 has coordinates 1/2 √3 over 2, and then so pi 2/3 pi is right here, and the coordinates for this are you negate the x coordinate and then just keep the y coordinate the same. So -1/2 comma √3 over 2. And then the reference angle, remember the reference number is the shortest arc length from that point to the x-axis. Well, you have this arc length right here, and then you have this one. This will be the shortest. To find this distance right here, you remember distances are additive. So remember, this distance right here, we're told is t, which is 2 pi over 3. And then this distance right here is the arc length that we're interested in. And that's, I mean, not the arc length, but the reference number. And that's t bar. And that should add up to pi. So we can solve for t bar, and that will be pi minus 2/3 pi, or pi minus t, and t is 2/3 pi. And then when you subtract this, you get pi over 3. So the reference numbers is pi over 3. I won't go through the next problem because it's basically the same. So I'll just leave that up to you. Just save some time. I will just, for 14, just because this video is kind of getting long. I won't go through all of them. I'll go through the first two, and then I'll leave the other ones for you. So I'll go through the first two, and I'll give you an idea how to do the rest. So number 14, I'll do part A with you guys. So we want to calculate sine of negative 13 pi over 4. Remember first, so when you have a negative number like this, that means you go clockwise along the circle. And so you could work out the coordinates and do that way. Or you could just remember that the sine is an even function or an odd function. So you can kind of factor out the negative in a sense. So you can bring the negative out into the front and then you get that. So now we just kind of work out what 13 over what point corresponds to 13 pi over 4. Well, the way to do this is to take off as much. You want to break off 13 pi into some multiple of 4 and then some remaining piece. Well, we can do it like this. And then we can divide the 4 into this, so we get 3 pi plus pi over 4. So 3 pi means you go around. So let's just figure what that means. So 3 pi, if you have your circle, is comprised of 2 pi and then pi. So pi means go all the way around the circle, and then you now go around a distance of pi. And then pi over 4 means you're going to land in somewhere like here in this third quadrant. So this will be, this point on the circle will correspond to 13 pi over 4. So 13 pi over 4 corresponds to the third quadrant. So we just need to know the coordinates of pi over 4 and then put the appropriate signs on the coordinates. So pi over 4 is the easiest one to remember. It's just root 2 over 2, root 2 over 2. So the coordinates of this point are going to be in the third quadrant. X and Y are negative, so you put negatives on both. And then by definition, so sine of, let's just write down the calculation again. Sine of 13 pi over 4 is the same thing as negative sine of 13 pi. By definition, sine of some number is just the y coordinate, and the y coordinate is this, but then we have this negative outside, so it cancels. So you get root 2 over 2. And for B, I'll just do B with you. So first of all, we have this number 15 pi over 4. We want to do, oh man, I did this wrong. Didn't I? It was supposed to be, okay. I was supposed to do 13 pi over 2. Well, anyways, this is basically the same prop. So here you go. There's 13 pi over 4. So I kind of mixed up part B and part A and part B. But anyways, 15 pi over 4 is the same thing. You want to split this up into some multiple of 4 and then some remaining piece. So we can write this as 12 pi plus 3 pi. And then 4 into 12 pi gives me 3 pi. And then, actually, is this the way I want to do this? Yeah, okay, I can do it this way, yeah. So let's draw this on the unit circle. Again, you don't have to do all this stuff. You can, it would be good to break it off in this way to figure exactly how much, to figure out where on the circle you are, but you don't have to go in this much detail. Because I know when you take an exam, you're limited on time. So 3 pi means you go around the circle once and then you go halfway around. And then 3 pi over 4 means you don't quite go a whole pi around. So you don't go halfway around the circle again. You just kind of go 3/4 of the way. And so that's going to end up, you're going to end up over here. You should land in the 4th quadrant. And if you're not sure how to see that, you can just compare the number to 3 pi over 2. So the claim is this, that 3 pi over 2 is less than 3 pi over 4, and probably obvious, but if it's not, maybe this helps. So proof. Well, this is the case if and only if I can cancel some stuff out. So I can cancel the 3 pi's out. So I get 1/2 is less than 3. Oh wait, this is not right. I'm screwing something up. Hold on. This is dumb. Why am I making this mistake here? Okay, sometimes, as you can see, and I tend to make arithmetic errors, which is why I don't fault you for making arithmetic errors. So I'm just trying to figure out, why is this not working out? I thought it would be. Yeah, so you're in the, oh, I know why. Okay, I'm comparing the wrong numbers. So if you go, so we want to, the claim is that this point corresponds to a point in the 4th quadrant. So for that to be the case means that 3 pi over 4, the distance you travel from here to here, this 3 pi over 4, is greater than traveling just pi over 2, which would land you here, right? So what we need to prove is that pi over 2 is less than 3 pi over 4, and that's clearly true, right? That inequality holds if and only if I can cancel the pi's out first. So you get 3/4, and that's true. So because this inequality is true and it's equivalent to this inequality, we know that this inequality is true. So this proves that we do, in fact, when we travel 15 pi over 4, we do in fact land in the 4th quadrant. And so we can easily read off the coordinates for that. So again, if we're in the 1st quadrant, point of interest is the t-value of interest is pi over 4, and the coordinates for that are √2 over 2, √2 over 2. When you're in when you're in the 4th quadrant, the x coordinate is positive, but the y coordinate is negative. So we get √2 over 2, negative √2 over 2. And so cosine by definition is the x coordinate, and the x coordinate is this, √2 over 2. So that's the answer. And you go through basically the same procedure to calculate the rest of the parts. So it amounts to just identifying, like, you're given a t value. So in part C, you're given 2 pi over 3. Find the point on the circle that corresponds to that given t value. So you need to really just find the quadrant you're in, and then look at the coordinates of pi over 3, which is in the 1st quadrant, and just put the right signs on those. And then sine is by definition the y coordinate. So let's move on to the last few problems. So the last 2 problems are graphing So for 15, we need to remember the general form of a cosine curve. So the general form is the following. It's a times cosine of k times x minus b. A is the absolute value of A is the amplitude. And then B is the horizontal shift factor. In this case, we do not have horizontal shifts. Or this gives you the horizontal shift. And then the period of this function is 2 pi over k. So in our case, k is equal to 1/4. So it implies that the period is equal to 2 pi over 1/4, which is the same thing as 8 pi. So the function should not repeat itself. So we can look to rule out some options. We need to look at where the function is from. We need to look at the function on the interval 0 to 8 pi, and it should not repeat itself. But before we do that, let's get some more data. Let's look at f of 0. Well, when you plug in 0 to the function, so we want to just find out what's the y-intercept. That will help us rule out some options as well. So we plug in 0. So 1/4 times 0 is just 0. So cosine of 0. And then cosine of 0 is 1, remember. So we get 3. So 0, 3 is y-intercept. So the function, first of all, oh, and then also a is the absolute value of a is 3 is amplitude. So the function is bound between the lines -3 and -3. It does not repeat itself on the interval 0 to 8 pi. And the 0, 3 should be a y-intercept. So with those 3 pieces of data in mind, we should be able to determine the graph. So first of all, let's use the intercept to rule out some options. So if you look at A and C, 0, 3 is not on the graph, right? B and C, for B and C, 0, 3 is on the graph though, see? Also notice C is not bound between, it doesn't touch the lines y is equal to 3 and y is equal to -3. It doesn't even go up to 2, see? It doesn't touch the line y is equal to 2. So we can rule out A and C based on the fact that they don't have the right y-intercept, but also C does not pass through the lines y is equal to 3 and y is equal to -3. So our only options are B and D. So they have the right intercept and they're bound between the lines y is equal to 3 and y is equal to -3. So we needed to look at the graph function over the interval 0 to 8 pi. If you let's look at D. So you start at 0 and you move, so you're at 3, then you go down, then you go up, and then you go down again and up again. So that means it's repeating itself on the interval 0 to 8 pi. So that shows that this function does not have a period of 8 pi. Now let's look at, so that means D can't be the option. And of course, the only option then is B. So we can just write down B immediately. But let's just look at the function over the interval 0 to 8 pi just to really drive home the point that it has the right period. If you start at 0, you go down and then you go up. And so it clearly does not repeat itself over 0 to 8 pi. But the pattern picks up again after you go past 8 pi, and that means by definition it has a period of 8 pi. So B, the answer for this is B. So answer is B. And to get that, we just needed a couple pieces of information. We needed the y-intercept, the amplitude, and then the period. the period is 8 pi, so that means that it repeats itself every 8 pi, or you can look at the interval 0 to 8 pi, and that will tell you that the graph shouldn't repeat itself on the interval, but the pattern will repeat after when you go beyond 8 pi. All right, let's look at 16 now. So 16 is a similar problem. So we have g of x is equal to 4 sine 1/6 x, so 1/6 x, or just x over 6. So the amplitude is 4. So it should pass through 4. I mean, it should pass through the lines y is equal to 4 and y is equal to -4. And then the period is 2 pi over 1/6, which is 12 pi. So that means we want to look at the interval from 0 to 12 pi and determine whether a given option repeats itself or doesn't. If it repeats itself, then that option is not the graph of our function. But if it doesn't, it could be. For this, we also just want to remember the general sign, the plot of a general sine curve. So let's just remember plot of sine x. So sine x looks something like this. So it starts at 0 and it opens up. It goes up and then down. So first of all, because of the general form of the sine curve, we can rule out options C and B, because when you go to the right, the function goes down. Same thing for C. When you go to the right, the function goes down. The function is supposed to go up. So the only options are A and D. Now we just need to determine whether A and D is the right option. So let's look at D. So over the interval 0 to 12 pi, the function shouldn't repeat itself, but it's pretty clear it does. It goes up, then down, and then up again, and then down. So this will be a sine curve. D will correspond to some sine curve, but the period won't be 12 pi. So the only remaining option is A, and it does in fact satisfy the property that has a period of 12 pi, because when you start at 0, it goes up and then down, and then it goes up and stops right there, and then the pattern repeats. So the answer, whoops, for, oh my God, sorry, computer's wow, acting a fool. So the only option is A. So let's see. Is A. So for this one, we needed the amplitude, the period, and then just to remember the general plot of the sine function. For 15, we didn't need to really remember the general plot of cosine, but it wouldn't hurt to know that. So definitely know the general plots of the cosine, the sine, and even the tangent function. So for 15, we just needed the period, amplitude, and then just to find the y-intercept, and that helped us rule out all the options but one. And then for 16, we needed to know the amplitude, the period, and then just a general plot of the sine. Now so the last problem is 17. So let's do this one quickly and then call it a day. So for A, we want to calculate cosine inverse of -1/2. Well, remember how this works. So cosine inverse of 1/2 is going to be some number y. We don't know what, but we want to determine it. Well, y is that number such that cosine y is equal to -1/2. So we need to remember our unit circle. And again, draw the unit circle again. I'm not going to go through it, draw it, but we need to find, so remember cosine inverse is a function from 0 to pi to the interval -1 to 1. So we need to find a t value. We need to find a value of y in this interval right here. And it needs to satisfy the property that the y coordinate corresponding to that number between 0 pi and pi is -1/2. So let's look at the unit circle again. Draw the unit circle. So what we're interested in is a y coordinate, an x coordinate of 1/2. Well, that is right here, or -1/2. So it's actually going to be some variant of pi over 3. So it's not going to be pi over 3 because the coordinate is 1/2, and we're interested in -1/2. So really the option, the only angle between 0 and pi that satisfies the requirement is 2 pi over 3 because the x coordinate is -1/2. So we can immediately conclude from this, or from this equation, we can conclude that y is equal to 2 pi over 3. So that implies that cosine inverse of -1/2 is equal to 2 pi over 3. All right, so that's part A. Let's do B. So now we want sine inverse of √2 over 2. And that's going to be equal to some number of y. What is y? Well, y is that number such that sine of y is equal to √2 over 2. Well, y can't just be anything. Remember, the sine inverse function is a function from -pi over 2 pi over 2, and it maps into the interval -1, 1. So we're looking for a y value in this interval right here. And then the y, or this is kind of confusing. Actually, it is confusing. Let me call this t. I should have called the other one t. So we're looking for, so sine inverse of -√2 over 2 is going to be some number t, and t is such that sine of t is equal to -√2 over 2. So we need the y coordinate corresponding to this t value is -√2 over 2. So let's look at the unit circle again. So we're looking at t values that give us points in the first or the fourth quadrant. And the y coordinate is negative, so that means we need to look for a t value that gives a point in the fourth quadrant. So we need -√2 over 2. Well, you can see it's this one right here, 7 pi over 4. So t is going to be 7 pi over 4 because the y coordinate corresponding to it is -√2 over 2. So from here, we can conclude that t is equal to 7 pi over 4. So that implies that sine inverse of -√2 over 2 is equal to 7 pi over 4. Wait, something's not right actually. Because that's not in this interval, is it? No. Oh, we want the okay. It's going to be, and it's not going to be 7 pi over 4. That's the point we want, but we want to use negative angles now. So t is actually going to be equal to negative pi over 4. So that means that implies that sine inverse of negative root 2 over 2 is negative pi over 4. So that's the whole practice exam. As I said, the actual exam won't be as long. Hopefully that was helpful, and you can, of course, take the practice exam to the tutoring room. You can come to office hours, and I can go over it with you. And so watch this video, go through the practice exam on your own. Problem if you get stuck on, if the video is not quite helpful and you're still stuck on some problems, come see me or go to the tutoring room. You're allowed to take this practice exam to the tutoring room. So let's turn this off because I've had enough of this.